Well, hello there. I am back. We are embarking on a journey into chemistry. So, to jump into the biology that we need in Bio 156, we first need to lay down a foundation of chemistry. Because, after all, organisms, living things like us, are fundamentally chemical beings. Everything that sustains us, everything that gives rise to the properties of life in us has to do with chemistry. So we've got to understand some basics of chemistry to be able to understand the fundamentals of biology. So we're going to tackle chemistry actually in two chapters. This one, chapter 2, the chemistry of life, goes over what we might call inorganic chemistry, chemistry that does not focus on organic molecules like fats and proteins and sugars. Once we do this, we'll move on to chapter 3, which is titled The Molecules of Life, and that does focus on the organic chemistry that we need. So we're going to begin our journey here by looking at this photograph, this image, and if you were transplanted here or teleported here, it might strike you that there's a bunch of dead trees. What happened here? Was there disease? Was there a fire? It doesn't look like much is burnt here. What happened? What's going on? So the answer lies in chemistry. What caused this was acid precipitation, acid rain, acid snow, but precipitation coming out of the sky that is acidic, as potentially lemon juice. And this is caused by atmospheric pollution, which of course is chemistry. So we're going to come back to this issue. We're going to come back to this observation, this dead forest, and revisit an explanation of what happened here once we get some background in chemistry. So here we go. Let's move on. So before I talk about the specifics on this slide, that is the subject of matter, let me first make a comment about science and what we know in chemistry and how we approach learning things like chemistry in a class like biology, Bio 156. Well, chemistry, just like biology, is made up of facts, things we know, things that have been observed, documented, verified. And those are relatively easy things to learn. It takes time to memorize them, get them in your mind. And then there's processes, there's mechanisms, there's explanations for how things happen, how things work, what makes things happen. And those processes can be much more complex and a little more difficult to wrap your brain around. What we have here on this slide is a body of facts, is a body of observations that we know about, a little bit about basic chemistry and humans. So that's how we're starting here. So a fair amount of information for you to get up here. Now, what we'll encounter a little bit later in this PowerPoint is a discussion of chemical bonds and why it is that there are different kinds of chemical bonds and how they occur. So that's a more process-oriented subject, a little more challenging to wrap the brain around and understand. So we'll get there. We have both aspects of science here in this chapter, every chapter. So we're getting started here. Matter. Matter matters. What is matter? Anything having mass and taking up space. That's a standard definition of matter. So I have mass. I can climb on a scale and see it, show that I have mass, and I take up space. Sometimes there's not enough room for me and someone else in a small room. So I have matter. Anything of substance has matter, is made up of matter. Now matter, the substance of our universe, is made up of elements. So here comes another definition. An element is a substance that cannot be broken down into simpler substances by normal chemical processes, normal chemistry. So there are lots of different elements, basic chemical substances like this, can't be broken down into anything more simple, in our universe. They make us up. So as a matter of fact, there are 92 naturally occurring elements that scientists, physicists have observed, documented, and verified. And of those 92, and by the way, there's a figure here over on the right, and it lists some of those 92. In fact, it's highlighting those elements that make up most of our body, make up most of our mass. And you can see the percentages there. You are 65% oxygen. You're almost 19% carbon, etc. You can look down that list. You don't need to memorize those percentages. Now, of these 92 naturally occurring elements, 25 of them are essential to animals. Essential means that if an animal does not have access to these elements, cannot ingest them, take them into their body, then the animal will die, cannot survive. So we're no different. We need those 25. We are animals. Now, about 11 of those 25 make up 0.1% of our mass, very tiny percentage of our mass, or more. Okay, so make up 0.1% of our mass or more. So that's shown on the right-hand side. So some of them you don't need much at all, but they are critical and essential to life. And those are called trace elements. Trace elements. Anything that makes up less than 0.01% of an organism's mass is a trace element. Fluoride is one example. You have to have fluoride in your body to help prevent tooth decay. And so what do we do? Because some people don't get enough fluoride. Well, we add it to water. We add it to toothpaste, mouthwash. So a variety of ways to try to make sure people get enough fluoride so they don't suffer any consequences. Iodine is another trace element that you need to have enough of, or you can have thyroid problems, your neck, and leads to some serious illnesses. Iodine is often added to salt, like table salt, so that way people get enough iodine. So this is just an introduction to what matter is, what elements are, how many different elements there are, and which ones are important to us. So we're still on this subject of matter in section 2.1 of your textbook, but now we're specifically shifting our focus to the subject of atoms. So all matter, all substance, everything makes up my body, anything of substance behind me on the wall, bookcase, the plants, all kinds of things, the air in this room, all matter consists of tiny little particles called atoms, and the atom is the smallest unit of matter that still retains the properties of an element. So for example, you could identify or isolate an atom of carbon, one little particle that represents that element called carbon, and it has the properties of carbon, the chemical properties of carbon. Likewise, if you're holding an aluminum can, then that aluminum in there is one of the elements. So that can is made up of however many gazillion atoms of aluminum. And each one of those atoms, each one of those tiny particles has all the chemical properties of the element aluminum. So that's the atom concept. And you can see on the figure that I've pasted on the slide here, it's depicting an atom of hydrogen and an atom of carbon. So we'll go over what those components in the pictures mean as we go over the slide. So what makes up an atom? What's kind of the anatomy of an atom? Well, in the middle of an atom, in the middle of every atom, we find a nucleus. And the nucleus consists of what are called subatomic particles. particles that are smaller than an atom. And there's 2 of them that can be found in every nucleus. Particles called protons and particles called neutrons. And every atom has at least 1 proton, at least 1, no exceptions. And the vast, vast, vast majority of atoms out there and around us have at least 1 neutron. Now, protons and neutrons are of about equal mass. So that means if I was holding a proton in this hand and I was holding a neutron in this hand, they would look exactly the same in terms of their mass, like 2 apples or oranges that are of an equal size and mass. Electrons are the 3rd kind of particle, subatomic particle that makes up an atom. So we have protons, neutrons, and electrons. And the electrons are really, really small, really tiny compared to the protons and neutrons. In fact, they're about 1/2000th of the mass of a proton or neutron. So imagine like holding an apple in my hand, that's a proton or a neutron, and then cut out 1/2000th of that apple, like a tiny speck, and that would be an electron. So they're really small, and they surround the nucleus. They're kind of far away from the nucleus, from the atom's world, and they're kind of swirling around the nucleus in a cloud of electrons. So that's a concept, a sort of picture to have in your head. The protons in the middle have a positive electrical charge, and the electrons have a negative charge. So they're attracted to each other. Positives and negatives attract. The neutrons in the nucleus don't have any charge. They are neutral. Okay, all atoms of a particular element have the same number of protons, and that's called the atomic number. In fact, the atomic number is essentially the definition of each element. So, for example, hydrogen, in a periodic table of elements, all hydrogens have 1 proton in them. That's it, 1 proton. That is the atomic number for hydrogen, 1. If an atom has more than 1 proton, it cannot be hydrogen. It has to be something else. In fact, if an atom has, say, 6 protons, then it represents carbon. It has the chemical properties of carbon. Every atom that has exactly 6 protons has an atomic number of 6 is carbon. So that's how it works. Now, the last thing here is the idea of atomic mass. Atomic mass is the total amount of mass that makes up an atom, and the atomic mass is made up of the number of protons plus the number of neutrons, because they're about the same size. And we leave out the number of electrons because they are so tiny, so minuscule, 1/2000th of the others, we leave them out of that calculation. So that's the difference between atomic number, that's the number of protons, that defines the elements, and atomic mass, protons and neutrons, the total amount of substance in an atom. So now we're going to focus our attention on electrons. Why? Because electrons are the parts of atoms that are responsible for their chemical properties, like their chemical behavior. It's mostly about electrons. So we need to focus on them a little bit. Electrons are found, it's a concept, it's an idea, are found in what are called electron shells. These are like spheres, globes around the nucleus of an atom, and these shells are where the electrons are found, spending their time. More specifically, these electron shells have very specific areas where electrons are spending time, and those specific regions where the electrons are spending time are called orbitals. Those are the places, those are the spaces that fill up with electrons around an atom. Now, atoms that have incomplete electron orbitals, that is, another way to translate that is the shell, the outer shell of electrons around an atom, if it's not completely full, incomplete, those atoms are the most chemically reactive. Those are the ones that we encounter the most in the subject of chemistry, are ones that do not have their outer shells filled with electrons. So that's going to be a focus here. Remember this. Atoms will lose, gain, or share electrons in order to help completely fill their outermost shell. So it's kind of like you being hungry. Your stomach is a little bit empty. It's like you're going to look for food. Your brain is telling you, I need food, I need food. When you put food in there, your stomach's full, you'll be content. You can then think about other things, hopefully. So it's somewhat the same with atoms. If their outer shell isn't full of electrons, it's like their stomach isn't full of food, they search for ways to make their outer shell full of electrons, and we'll get to that soon enough, and that helps to fill their stomach, and then they're not reactive. Here's some important notes about electrons that you need to know, some facts, okay? The very first shell, the very first sphere that's around the nucleus of an atom holds exactly 2 electrons. When that shell is full of 2 electrons, then a second shell would have to start filling up outside of that one. First shell holds 2. The second shell, okay, the shell that's outside the first one, holds up to 8 electrons across the board, throughout the universe, all atoms. And when that one is full, then a third shell outside of that one begins to fill up. These are some properties across the board of how atoms behave. Look up at this little snapshot of part of a periodic table that I put onto the slide. So if you look in the very upper left corner, it says hydrogen. And what it shows you there is a little orangish dot on the outside of that hydrogen atom. That's its 1 electron. The number 1 that you see next to the H in the hydrogen box, that's actually the atomic number. That's telling you the atomic number for hydrogen. So it's telling you that hydrogen has an atomic number of 1, has 1 proton. And having that knowledge, how many protons are in the atoms, that tells you how many electrons are going to be outside in the shells. So there's 1 proton in a hydrogen atom. There's 1 electron outside in a little orbital in a shell. Now look across that table over to helium. Okay? Helium. You see a number 2 next to the He. What does that number 2 mean? It means helium atoms have 2 protons. Where? In their nucleus. All helium atoms have 2. That's the atomic number. That's the definition of helium. Now, because there's 2 protons, how many electrons are going to be outside of that in that first shell? 2. It's going to match up. So for helium, its shell is full naturally, which means it's not reactive. If atoms have more than 2 electrons, then you look down in the second row of that diagram, those atoms are now working on their second shell to fill it up. And the concept continues going across the rows. So atoms make bonds with other atoms as they try to fill their shells, and we're going to get to that shortly. Remember from chapter 1 that energy was a key concept, key theme in biology, energy processing. Organisms need to process energy in order to sustain life. Well, energy originates with atoms. And the energy that life uses, the energy that life taps into for growth, movement, reproduction, all these kinds of things, that energy is located in the electrons of atoms. So any sort of concept or understanding of how life, how organisms use energy in biology, requires one to dive down at some point to the level of atoms. And that's what we're doing right at this moment. Electrons are associated with energy. Now, electrons have what is referred to as energy of position. And energy of position is potential energy. So let me remark on that. Potential energy is stored energy. It's energy that's not being used, but it has the potential to be used, to do something, to make something happen. So, one clear example of potential energy is a gallon of gasoline. It's full of chemical energy. The chemical bonds, which the electrons, exactly what we're talking about here, are full of lots of energy. That energy is not being used for anything in that gallon of gas. It's just locked up in those molecules. Okay, so that's potential energy. Now, energy of position, okay, that the gallon of gasoline is not an example of energy of position. That's an example of chemical energy. Energy of position refers to things being higher or lower, essentially. So if you're standing on the ground, then you have very little potential energy with respect to your position. If you trip and fall, you might get hurt, but hopefully you'll be okay. If you're high up on a 10-story building on the roof, well, you've got a lot more energy of position. You've got a lot more potential energy because of gravity and your relative position to the street down below. So that's energy of position. Now, electrons occupy different energy levels or electron shells in an atom. I've mentioned electron shells. And depending on which energy level, which shell the electrons are in, that determines how much energy that electron has. The farther an electron is from the nucleus of an atom, the farther it is, the more potential energy it has, the more energy of position, the more energy it would release if it fell towards the nucleus. An electron that isn't so far away from the nucleus, that's in a lower shell, will have less potential energy. So this will be a phenomenon that'll be sort of in the background, hopefully in your thoughts, and we might refer to this again when we're talking about metabolism and energy later on in biology. So it takes energy to move electrons out to farther levels, farther shells. Energy is released when the electrons fall back towards the nucleus. So we're in section 2.2 here, and the topic is introducing ions and isotopes. So we're still on the subject of atoms, really, and so these are variations of atoms, okay? Variations of atoms. So what is an ion? Just defining an ion for you at the moment, and we're going to come back to them in a few slides when we start talking about chemical bonds. Because one of the kinds of chemical bonds is the ionic bond. So you're being introduced to what an ion is here. So an ion is an atom. It could actually be a little cluster of atoms, but atoms that have gained or lost one or more electrons. That's it. That's the definition. That's an ion. You should know this. If you look carefully at the figure on the upper right-hand side of your slide there, I can move my camera down, I guess, while I'm talking. There's a picture of sodium. Sodium's atomic symbol is Na. That's how we represent sodium, Na. And sodium ion or sodium atoms have an atomic number of 11. What does that mean? It means that sodium atoms have 11 what's in their nucleus? Protons, 11 protons. So if they have 11 protons, then how many electrons are going to be going around that nucleus in shells? 11. They match up, protons and electrons. So map out the electrons. Look at the picture. It's drawn for you. How many electrons fit in the very first shell around the nucleus? We went over this. 2. Out of those 11 electrons, how many fit in the second shell? 8. Count them up there. So now we're up to 10. The 11th electron needs to be placed in a third shell, farther away. Now, sodium very commonly exists in an ion form. So what happens is that outer electron, that electron that's on the very outer shell, the third shell, it moves to a different atom. It transfers to a different atom for a reason we'll get into in a little bit. But when that electron leaves, then that sodium becomes positive, has a positive charge. How come? Let me quickly tell you. How many protons are in that nucleus of sodium again? There's 11. Once that electron left, how many electrons are around that nucleus? There's 10. So that means there's one more proton in this atom than there are electrons. And if there's one more proton, that means it's got a positive charge. Now, the other thing that's defined on this slide is isotope. Isotope, very different from ions. Isotopes are atoms that have the same number of protons, so that means they belong to the same element, but they have different numbers of neutrons. Those are called isotopes. Most elements in nature, in the universe, exist as a mixture of different isotopes. There's an example on the bottom of your slide. The example is of the element carbon. So carbon always has how many protons in its nucleus? We've mentioned this a couple slides ago. 6. It has an atomic number of 6. So every carbon atom has 6 protons. But look at the picture on the bottom. It's showing you 3 different variations of the carbon atom, 3 different isotopes. One of the versions on the far left is carbon 12. 12 is its mass number. So it's got 6 protons always, but in order to be a carbon 12, it's got to have 6 neutrons. So that's the most stable form of carbon, is carbon atoms that have an equal number of protons and neutrons. But there are also carbon 13s out there. Carbon 12 is by far the most abundant. Carbon 13s, they still have 6 protons, because carbons all have 6, but there are 7 neutrons. So that makes carbon 13. And if you I ask you, what's carbon 14? What does the 14 represent? How many protons are in there? 6. But if it's 14, how many neutrons are there? It's got to be 8. So that's a very rare one, carbon 14. It actually forms high up in our atmosphere. So those are isotopes. Let's take a little more of a look at isotopes. So as I said a moment ago, a little bit more about isotopes. You need some relevance to our biology, especially human biology. So some isotopes are unstable, and they break up into particles that have lower atomic numbers. This process of breaking up like this is called radioactive decay. And this is what gives rise to radiation. Like when you hear about a nuclear weapon or a nuclear power plant or a disaster at a nuclear power plant and there's radioactivity, that radioactivity is energy that's given off, very powerful energy that's given off when these isotopes break down and undergo radioactive decay. Now, most of the isotopes in our universe are stable, like carbon 12. It will always be carbon 12. It's going to stay that way forever. But there is, for example, radioactive carbon 14, as I mentioned, that forms high up in our atmosphere. And that carbon 14, when it decays, when it kind of breaks down, it turns into nitrogen 14. Having one more proton than carbon, and so the balance of protons and neutrons shifts. And Carbon-14 has a known rate that it breaks down into nitrogen-14. It's just a little over 5,000 years. It takes a little over 5,000 years for half of a sample of carbon-14 to break down, for a whole sample of carbon-14 to break down so that only half of it is left. It takes a little over 5,000 years. And then it would take another 5,000 years for that remaining half amount of carbon-14 to break down again in half, and then you'd have quarter the amount. And then it would take another 5,000 and something years for half of that to break down. That's the concept of half-life. And this is how we date and figure out how old fossils are, is using these properties of radioactivity to estimate how long something's been dead, as we look for the proportion or the amount of radioactive isotopes compared to stable ones. So that's one important application of radioactive isotopes to biology, is that we can figure out how old rocks are and fossils are. We can figure out how old the Earth is, how old our, Earth is, and know a lot about our history. Now, another application of radioactive isotopes is in medical procedures where they're used, for example, as tracers. So tiny, tiny amounts of radioactive isotopes are injected into a patient, and those radioactive isotopes can accumulate in certain areas of the body and indicate if there's a disease or a problem or an abnormality, such as finding cancer, which is shown in the figure here on the right-hand side of your slide, where the radioactive isotope is accumulated and shows cancer in the head region. It looks like a patient. Now you can look down on the bottom of the slide. You do not need to learn all those details, but I simply wanted to give you some examples of medical radioactive isotopes and what they're used for. Again, you don't need to know the specific examples. Maybe give one of them. I should say that. Like, give one example of a radioactive isotope and what it does, but you don't need to know the whole chart. And so I don't need to read them all. You can take a look at them, but they're very important in the medical field, radioactive isotopes. So now we're switching. Now we're in section 2.3, your textbook, and now we're switching to the concept of molecules. Remember that hierarchy of life? Chapter 1, something we focused on. Help us get a grounding for biology. Atoms are at the bottom of that hierarchy, and then atoms fit together to make molecules. That's where we are in our hierarchy of life, is now we're focused on what are molecules, how do they form, where do they come from, etc. A molecule is a definition. You need to know lots of definitions. Is a group of atoms held together by energy in the form of a chemical bond. There are three main principal types of chemical bonds that you need to know about, I need to know about in biology. And they are ionic bonds, covalent bonds, and hydrogen bonds. I got this image off the internet. I search for images sometimes, and that metallic bond is not something we need to know about in our biology here, so I X'd that out. Now, in the covalent bond category, I will review this, I will explain this to you. There are polar covalent bonds and nonpolar covalent bonds, and these are all important, all very big relevancy to biology. So let's dive into the world of molecules and chemical bonds. So the first one that we're going to tackle here, entertain here, is the ionic bond. The ionic bond, that's the name of it. And the ionic bond involves the attraction of oppositely charged ions. Remember ions a couple slides ago when we were in the topic of atoms, and I gave you a brief definition? An ion is an atom that has lost or gained electrons, and it becomes either positively or negatively charged. So if you have one ion that is positively charged and another ion that is negatively charged, they will attract. And that attraction is an ionic bond. That is what an ionic bond is. They stick together kind of from their attraction. So ionic bonds, for example, hold sodium and chloride ions together to make salt. So I'm looking at this figure right now. It seems like there should be a little bit of text on this figure. So let me lead you through it. There's no text on this figure. So on the upper part of the figure, maybe you can see my cursor moving around. I'm not sure. This would be a sodium atom. How can I tell that? Well, I can tell that because there are 11 electrons. That's how I can tell that. And I can tell this is a chlorine atom. There would be a Cl in the middle because this has 17 electrons. It has 17 electrons because there's 17 protons in the middle. There's 11 electrons because there's 11 protons in the middle. I'm just using my knowledge, stuff that I'm teaching you about, atoms to be able to deduce these things, observe these things. So look, we follow this purple arrow down, and what it's showing you is when sodium gives up its electron in its outer shell, and it moves and transfers over to chlorine, then that sodium becomes, like I said a couple slides ago, positive because it has 11 protons in the middle and now 10 electrons around it. And this sodium ion is actually more stable because the shell that has those 8 electrons in it is now happy. Like, ooh, I'm an outer shell and I'm full of electrons. Let's turn our attention to the chlorine. The electron from the sodium moves to the chlorine and it now fills up chlorine's outer shell. Chlorine's like, I'm full now. My outer shell's full of electrons. I'm happy. But what that does is it now gives that chlorine atom how many electrons? It had 17, now it has 18. But it still has 17 protons in its nucleus. So that means it has one more electron than protons. It is now negative. So now we have a positive sodium ion, a negative chloride ion, and what do? They attract, and voila, we have sodium chloride. We have salt. And it most commonly exists in crystal form, like you can do your salt shaker, see little crystals come out. It's basically these clusters of sodium and chloride ions that are all stuck together because they're attracted by their positive and negative charges, and those are ionic bonds. Now, before we go on to the covalent bonds, I want to tell you about electronegativity and how it relates to ionic bonds. Your textbook mentions electronegativity. I think I'm going into it a little bit more here because I think it helps you understand what's going on with this chemistry. So, electronegativity helps us understand why sometimes things form ionic bonds and why they sometimes make covalent bonds, etc. So it's a very important idea. What is electronegativity? Electronegativity is a measure of how strongly an element pulls on the electrons of other elements. It's very similar to how people have different strengths. So you have arm wrestling matches. Not everybody's going to match up equally. Somebody's going to be stronger than somebody else. So in a similar way, in the world of the elements in our universe, each element has its own strength, of how strongly it pulls on electrons from other atoms. And that strength is referred to as its electronegativity. And chemists figured out these electronegativities well over 50 years ago, and it contributed a lot to our understanding of chemistry. If you look at the periodic table that I put on this slide, got it from the internet, by the way. You won't see it in your textbook. Hydrogen is up in the upper left-hand corner, where it always is. and it has an electronegativity of 2.1. So that's the number given for its strength. That's not a very weak, a very strong element, but it's not the weakest either, as you can see by looking at some of the numbers. So that's hydrogen, 2.1. If you look down from hydrogen, you can find sodium. We just talked about sodium a moment ago. It's only 0.9. It's a pretty weak element. Now, if you look over on the right-hand side of our periodic table, you can see in the upper right-hand corner F for fluorine. And it is the strongest of all the elements. It has the highest electronegativity. It pulls on the electrons of other atoms the most strongly. And oxygen is right next to it. Very powerful, second most powerful. Now let's use this idea of electronegativity to explain ionic bonds. I have in green on this slide, if the electronegativity difference between two atoms is greater than about 1.7, then the electrons are going to transfer from the weaker to the stronger atom. And when that happens, it's going to result in the weaker atom becoming positive, a cation, and the stronger atom becoming negative, an anion. And then they attract. I think I'm going to apply this to the next slide where we turn back and look at sodium chloride again and see more specifically what is happening. So you can always go back and look at these electronegativity numbers, but highlight the fact before we move on that sodium's electronegativity is 0.9, and chlorine, which you can see on the right-hand side of the chart, is 3.0. So here we go. Electronegativity and ionic bonds. Trying to help you put it together to understand why this happens and how this happens. So returning to the formation of ions, how does electronegativity figure into the formation of salt? See if I can move my camera around here. Maybe it's not in a bad place. Keep it down in the corner. So let's begin with chlorine. Its electronegativity is 3. Just saw that on the last slide. And sodium is 0.7. It's actually 0.9. I got a typo on here, 0.9. So the difference between those two numbers, if you subtract 0.9 from 3, the difference is 2.1. Now, I just said on the last slide, if the difference in electronegativity is greater than about 1.7, then ions are going to form. So here we go. The difference between sodium and chlorine is 2.1. That's a pretty big difference. So that's why an electron transfers from the weaker sodium atom to the stronger chlorine atom. That's a big reason why. So now, having one more proton than electron, sodium becomes a cation, positive. Chlorine becomes an anion, negative. Opposites attract, and bingo, we've got sodium chloride. It's based in electronegativity. Alrighty, we're still in section 2.3, but now we're turning our attention from ionic bonds to covalent bonds. Covalent. If you looked up the word covalent, you'd probably find something having to do with sharing. A covalent bond forms between two atoms when they, that's the critical word, share electrons. So they're not transferring electrons. Electrons are not moving from one atom to another. That's ionic bonds. But atoms are sharing electrons. Now, every pair of electrons that is shared between two atoms, one electron with one atom, one electron with the other atom, each pair that's shared represents one covalent bond. So 2 electrons being shared makes one covalent bond. The number of electrons that are shared varies depending on how many electrons the atom needs to fill its shell. Let me say something about that. Some words here. Hydrogen. It's the simplest example. It's got one proton, therefore it has one electron. And if you remember, that one electron is in the first shell, and that first shell holds two electrons. So hydrogens need one more to get to two. That's it. Every hydrogen atom in the universe needs one electron. That's it. And every hydrogen will make exactly one covalent bond with another atom to get that electron. Now, if we turn to carbon, because I've mentioned carbon a few times now, carbon has 6 protons, has 6 electrons, and if you mapped out those electrons, the first 2 would be in the first shell, and then the remaining 4 electrons would be in the second shell. The second shell holds how many electrons total to be full? Holds 8. That's a number that all atoms have. Needs 8 electrons, and the carbons only have 4 in their second shell. Therefore, carbons need how many more electrons to get to 8? They need 4. They need 4 more. How many chemical bonds, how many covalent bonds will carbon atoms make to get those 4 electrons? They'll make 4. They need 4 electrons, they will make 4 bonds. So this is a theme that applies throughout the world of covalent bonding. The example on the bottom of your slide is with hydrogen. So you got 2 hydrogen atoms very close to each other. Each one of them has 1 electron in its outer shell. That's it. They each need 1 more. They need 1 more. So these 2 hydrogen atoms get together and they say, hey, I'll share my electron with you if you share your electron with me. If we do that, then we'll each have access to 2 electrons. It's kind of like sitting around a table with another student, and you each need 2 pens to do a project. And you have 1 pen, and you look across at the other student, and he or she looks at you, and they have 1 pen, and you're like, say to each other, hey, let's share our pens. Let's keep them in the middle of the table here. And if we share our pens, we can each have access to 2. And then we'll have what we need. So sharing gives you more. This is what atoms are doing. They are sharing electrons to help each other get more. So these 2 hydrogens share their electrons with each other, and now they have full shells with 2 electrons. That's how it works. In the world of covalent bonds, where atoms are sharing electrons, some covalent bonds are what we call nonpolar covalent bonds, nonpolar. That means they do not produce any kind of electrical charge. When you hear the word polarity, think of charge, like on a battery. If you don't put a battery in your appliance or flashlight or whatever in the correct way, the correct direction, you have the polarity switched because one end of the battery is positive and the other end's negative. That's polarity. If you put it in the wrong way, your flashlight won't work. All right. So polarity is having positive and negative charge. So here's a rule. If the difference in electronegativity between atoms is less than 0.5, then the atoms will share their electrons equally, and that will make what chemists call nonpolar covalent bonds, and no charge will develop around that covalent bond. So because they lack charge, there's no positive or negative around them, nonpolar molecules do not attract to each other like ions do. They're just like oblivious to each other. Look at the figure to the right. I pulled this, I think, off the internet. Yep. So it's showing you, again, a molecule of hydrogen gas. H2 is its molecular formula. It tells you there's 2 hydrogens in it. There's also an H with a dash and an H connected to it. that is called the structural formula. So the structural formula has lines between the atoms to represent the covalent bonds. It's actually something you should know. So every single hydrogen atom out there has an electronegativity of 2.1, which is something to memorize. And you can see that on the chart that I showed you a couple slides ago. So if two hydrogen atoms share electrons with each other, they're going to be exactly the same strength. They're both 2.1 electronegativity. So those electrons will be shared 100% equally. There's no difference in their electronegativity. So they will share 100% equally, and the covalent bond will be 100% nonpolar. So using hydrogen as an example gives you an idea of how this works. Okay, so now you know what a nonpolar covalent bond is. How about a polar covalent bond? Let's jump to that level. Now here comes another rule. These rules kind of fit together. A polar covalent bond will form if the difference in electronegativities is equal to or greater than 0.5, but less than that 1.7 cutoff. Okay, so there's a bracket there, 0.5 to 1.7. If two atoms differ in that range of numbers, then the stronger atom will have the electrons around it a little bit more of the time, making it a little bit more negative. And the atom that's the weaker one will have the electrons pulled away from it, not 100%, kind of tugging and pulling, and that atom will become a little bit positive. That's polarity. That's like a battery. One part being a little bit negative and one part being a little bit positive. So let's take a look at the water molecule that is in the upper right-hand part of your slide. So water is H2O. That's its molecular formula. You can see that underneath the diagram. It has two hydrogens and one oxygen that are bonded together. And specifically, the two hydrogens are stuck to or bonded to the oxygen. Now, oxygen's electronegativity. I could ask you to go back and look at that chart, but I'll tell you it is 3.5. Make a note of that. 3.5. You can even write it if you've got this printed out or whatever next to the oxygen. And the hydrogen's electronegativities are, do you remember? 2.1. Okay, so hydrogen's 2.1. If you do the math and figure out the difference between 3.5 and 2.1, you'll find out it's 1.4. 1.4 is in that range between 0.5 and 1.7. Therefore, oxygen's the stronger one. It's going to pull the electrons that are being shared towards it and make it a little bit negative. And the electrons are being pulled away from the hydrogen atoms, and that will make them a little bit positive. There's our polarity. The arrows in that diagram are telling you the electrons are being pulled towards the oxygen. Now, you see that little weird notation next to the hydrogens and the oxygen? That's called a Greek letter delta, lowercase d, delta. And it's used in science to represent a little bit or partial. So in chemistry, we use that delta symbol to mean a little bit positive or a little bit negative. So you'd actually see that written next to the atoms in the molecule. So there you go. That's how you get polar covalent bonds, is that the difference in electronegativity between the two atoms is between 0.5 and 1.7. They will not share equally. They still will share, but they won't share equally, and that will make the covalent bond polar. Here's a chart that I found. Well, there's a couple pictures here that I found that I think provide kind of a nice summary of what I've gone over to give you a visual of the spectrum of pure covalent to ionic bonds. So if you look on the left-hand part of this chart, it shows you look on the x-axis on the bottom, there's a series of numbers, and those numbers represent the differences in electronegativity between two atoms. So if you look on the left-hand part of this chart where the electronegativity difference is 0, that's going to occur if you have two atoms of the same element bonding together and sharing electrons, like two hydrogens or two nitrogens or two chlorines. They will share electrons 100% equally because they have the same electronegativities, and they will be pure nonpolar covalent bonds. Now, any difference between 0 and just 0.5 is going to give you still a nonpolar covalent bond, not a pure one, but it's going to behave like that. So the bond between carbon and hydrogen is a nonpolar covalent bond. It's in that range. Then if you look in the middle of the chart, difference in electronegativity from about 0.5 on up to 1.7, you see several examples there of polar covalent bonds between different elements. And then finally on the right-hand side of the chart, you see that 1.7 mark, and above that mark, the stronger atom gains an electron, the weaker atom loses an electron, and you get ionic bonds. So it's a visual, shows you a spectrum of what can happen. There's also a figure in the upper right-hand part of your slide that's kind of giving you a visual about how electrons are being shared or not under these different kinds of bonds. All right, you remember how many different kinds of chemical bonds we were going to cover? 3. Oop, this camera's in a weird place. Slowly learning. So here we go. The third one is the hydrogen bond. Hydrogen bond. And hydrogen bonds are between two molecules. So this is something different. They don't form molecules, but they are between two molecules. And they're very weak bonds. It's actually a weak electrical attraction. Here's the definition. A weak electrical attraction between the positive end of one polar molecule and the negative end of a second polar molecule. Okay, that's the extent of it. That's the definition. It's an attraction between two polar molecules. So each atom with this partial, little bit, delta, negative or positive, kind of acts like a magnet, oppositely charged to attract to each other. Take a look at the example I put in the upper right-hand part of your slide. There's a molecule of water, H2O. It's polar. We just went over that. And then there's a molecule of ammonia, NH3. And in fact, you could think through what makes it polar if you went back to our electronegativity chart and figured out what nitrogen's electronegativity is. Remind yourself what hydrogen's is. Figure out the difference. Then you can understand why nitrogens and hydrogens make polar covalent bonds. I'm leading you through this. And because they make polar covalent bonds, the nitrogen becomes a little bit negative and the hydrogens become a little bit positive. So ammonia is polar. So you've got a water that has hydrogens that are a little bit positive, and you've got ammonias where the nitrogens are a little bit negative. Those attract. Those are attracted to each other. And that attraction is a hydrogen bond. And how do we represent it in a diagram or a picture? With dots. That's your answer, with dots. So that way we can distinguish between a covalent bond, which is inside a molecule. Those are represented by straight lines. You can see them here in the picture. Whereas hydrogen bonds are represented by dots. Remember.